Okay, we should be live. Hello. Got lots of stuff to do today. Timeline is a mess. All right. Let's get some stuff done. We have a lot of interesting things to do today. So, let me go over just for a moment what I've been working on and some of my plans going forward. So, as I said before on stream, as a company, Puffer is officially open for business. All that means is that, I'm going to be spending a little of my time looking for and hopefully acquiring and doing some work for some clients. But everything's open source. I'm still going to be streaming lots of dev, and I've got lots of cool stuff coming for everyone as well. Speaking of which, we have these two games right now, right? You can play Snake in your browser. These snakes are kind of dumb, but they are running reinforcement learned policies in your browser, which is pretty cool. And then we have this, which we don't have the RL policies in here yet, right? But we have this MOBA game that runs in your browser, and it plays reasonably well. Maybe we have a few bugs to fix in it since this is a new port, since we had to port it in order to get it to run like this. Company page, no longer secret. But what I want to really build out over the next week or so. So as I said, I've had one more big simulator that it's in the works. It's going to take me a little longer to finish that. I ported 2,000 lines of stuff to C over Saturday. How are you running inference on web? Onyx Web runtime? Ho ho ho, no. No Onyx Web. We don't need any of that where we're going, my friend. Let me show you. That's actually what we're going to be working on today, is improving that. Snake. Where is it? Snake.h. Pure C implementation of the neural net. And we load the weights from PyTorch. That's what we're doing. So now this is not very impressive on its own, right? It's kind of cool that you can do this, but it's just an MLP. Now, the thing that I'm working on now, which is what we're going to be doing today. Oops, wrong one. PufferNet. Takes my hands a little bit to warm up typing. We have linear layers, comms, LSTM, and a few other utility functions, all in pure C. So we're actually going to be able to upgrade our web AI to be able to run pretty reasonably sophisticated networks. So the goal is going to be to finish this PufferNet thing, get it running the MOBA network, get it running the much better Snake network, and then the network for the secret project as well. And if we can do all of that, then we'll have some pretty crazy demos that will just run in your browser. I think that'd be pretty cool. Also, folks, if you have not started the repository, we are 2 stars off of 1K. It's all free and open source right here. So if you want to help me out, get us to 1,000 today, that would be awesome. I really didn't know if we were going to be able to hit this over the summer. This is crazy, the amount of growth. And I appreciate all the support on this as well. It helps to get the word out about this so that Puffer can get a little bit of revenue. And hopefully we can do some good work for some companies. And we can start investing more in our own infrastructure. I'd really like to start upgrading the Puffer cluster and start putting up some bounties for, open source contributors as well. 1K, 100th is awesome. 10K next. I mean, maybe. I don't know if there is an RL repo, like an RL library type thing with 10K on it. But that's enough yapping for now. I should, Interesting. Okay. I should actually start working on some of this stuff so you can see what's going on. I can't type. Whoops. It's Monday. This is what I get for taking a half day off for once yesterday. I needed a little bit of a break. Alright, so we go to Pufferlib. Ocean Porch. Okay, so this is the network that we need to port today. It's a little bit obnoxious because this network is a lot more complicated than I originally thought. No, this is a pretty complicated thing here. But we're going to see what I can get done on it. So we have Puffernet. And then we have this network that I started working on here. And I think that the big issue, if I recall, was just the data. Yeah, getting the data into a reasonable format, right? I think I figured out a workaround, though. I think I figured out a good workaround. So, CNN features. Yeah, so the way we're gonna cheat this a little bit. Obviously, these are all hard-coded. But what I'm gonna do is +3, and this is cheat continuous features at the end. And then I need to do a little bit of custom logic here, I believe. Because we take... Ooh. That's harder than I thought, actually, now that I'm looking at it. I wouldn't mind just doing this completely custom for right now, because if I just do it completely custom, I'm going to get something that's pretty simple, I would think. It's going to be a little trickier to test it. So let me explain what's going on through my head here. How's your weekend? Weekend's going good. Weekend went well. Ugh. I should be a little bit more rested than I appear at the moment. I'm like all messed up. Just need my coffee. But I did get some rest. So as soon as I warm up here, I should be cranking some good stuff. Let me explain a little bit of what's going through my head here and why this is actually kind of difficult. So essentially in PyTorch, you have this slice operation here, right, where I can slice tensors along various dimensions, and it makes it very easy. Now, I'd have to double check this, because it's possible they have some operations, but what you have to understand is that if you're slicing anything except the first dimension, depending on the memory format, but usually, hey, welcome. Usually, if you slice anything except the first dimension, you're actually going to incur a copy of the data. And you actually have to do some complicated operations behind the scene in order to copy the data along the specific dimension that you want. Now, I could implement that similar slice logic in C, and maybe it would be even a good idea to do that. But at the same time, this is kind of an opportunity for me to rethink a little bit how I'm making these networks, because this is slow, right? This is really slow. And ideally, what we should be able to do here is rewrite this network a little bit to just be faster, and not to have these copy operations, which would then make the C code a little bit simpler. So I'm trying to decide if I want to like mess with the pufferlib network code first, or if I want to mess with the C code, or how I want to do this. Because the more I look at this, right, the less I like it. Like, the observations are stored as flat data. So these last 26 elements here, this gets your memory to be non-contiguous. So right here, this is a copy. This view is fine. And then one hotting. So this is at least right here, this is a copy. And then this is another copy. And then this is a copy. Like, you can see we're just copying the data all over the place. That's a big problem. That's a very big problem. The thing that's tricky about this is that there's pretty much always a way to do it where you're not going to be copying all the data all over the place. But it's almost always going to require you to write like custom kernels, which I know how to do in C. I don't know I mean, I could look at doing my own CUDA kernel for this. I'd rather not have to do that. But, yeah. I really do want this network to be efficient. I'm trying to think how... Yeah, like, there's no way that that's contiguous, right? Hmm. Mm-hmm. It's actually funny because now that I'm looking at this, I know how to do it in C. I don't even know how to do it in PyTorch. You need to be able to write loops, right? I was thinking about over the weekend as well whether it's actually possible to come up with just a more efficient network design so I don't have to do all of this. But that seems unlikely to me. Because, like, you're pretty much... The reason that the data looks like this is that... I'm going to bring up, since I see we have people joining here, let me just bring up the diagrams here. Let me just write this out real quick so you can understand the problem. And maybe this will get me to understand a little better. Raw online. Let me show you what the problem is here. Oh, okay, perfect. It saved our image. So if you look at this as being like a 2D block of memory, where like if you look at this as a 2D block of memory, where like this way is the columns, right, and this is your batch size. So this like first row here is your first observation. Then what ends up happening is like we have in this data, this last chunk right here is going to be equal to extra data, which is data that is gathered from your specific agent, right? So it's like hidden stuff that your agent knows about itself that the other agents don't know about it. You're pretty much always going to need some data of that type. And then what this chunk is at the start is local 2D map data, which is data that is the agent can see from nearby, right? And I have two different types of data in there. We can kind of ignore that as an implementation detail for now. But technically, there are two different types of this data in these blocks. Now, the problem is this is not how contiguous memory works, right? This is contiguous. This chunk here is not. So if I want to split these out, I have to do a copy of the data. And then, whatever I do with it, depending on how I do that, can incur additional copies. And we have this long pre-processing process where eventually we just want to convert all this data into a nice contiguous block. And the issue is that, like, I know how to do this if I'm going to write custom loops for everything. I know how to do that. So I can do that in C and make sure that the web networks are reasonably efficient. But then the PyTorch networks, which are more important that they be fast, are harder. Can you help me? I want to implement RL for a simulation. RL with some pre-trained model and use the knowledge to explore. Similar to humans. That is hard. RL 4 is... It depends what simulation. Like, are you building a simulation for this? Or are you using an existing one? It depends what you're doing here. Well, I think that the most practical way of doing this, assuming that I don't want to start writing my own custom kernels for networks just yet, that seems a bit overkill, is going to be to look at the design of this PyTorch network and see where I can cut out some of these copies, potentially. So I have to just confirm. Slicing creates a view, right? Tensor views. Do they actually have some efficient stuff on this? Ah, okay, I see. So maybe I don't have to worry too much about this. Where should I look for that? I mean, Neural MMO is kind of one. It's a more complicated environment. You can look at, like, if you want inspiration for stuff, you can look at works like Xland. Um, I'm trying to think of other ones. People did like this Xland mini grid thing that's like not really all that complicated, but it's has some of those properties. Um, New solutions in simulation, similar to humans. I mean, that kind of happens if you run it for long enough. Though typically, if you want it to keep exploring and keep developing new things, it needs to be able to update its model. Because, like, RL models don't have, we don't have amazing methods of memory at the moment. So, like, you kind of need to keep learning, right? So if you think about it, like, the thing that's similar to humans is actually kind of just doing online RL in the first place, right? Like, humans aren't fixed. We're allowed to learn. So it's like the more realistic thing, if you want to look at it that way, is to just keep training and look for stuff where it can keep finding new solutions, which is the definition of open-endedness. So it does look like PyTorch has some operations here. Uh, Outputs are unnecessary. Avoid unnecessary data. Okay. Yeah, this is very odd because you actually, I can't tell here. This is interesting that they say their split operation does not, like, their split operations don't actually affect memory. They don't actually copy. But I think that as soon as you go to do anything with that data, right, of course it has to copy it anyway. So let's say that I split this, and then I one hot it. split, view, split, one hot. That's so freaking complicated, though. Really don't like that. You know, I really want to be able to have an architecture here that isn't like this crazy beast of a thing to optimize. And this is adding complexity to stuff. I guess technically there is another format I can consider, though I don't know if it makes it any easier. I guess it kind of makes it easier in the sense that, like, if I commit to this type of an architecture, then I only ever have one thing to optimize, but I don't know if the architecture itself is very good. If you commit to either having everything be discrete or discretizing everything, so that, like, each type of observation you have is discrete in some way, then you can pack everything into an integer. I don't know if that's better. I should probably also make this in view. Can we use the same network to train on multiple different simulations? Build up some general knowledge. So the general rule on that is you can probably train on different simulations, but only if you have a lot of different simulations. If you have like n equals 2 simulations, that's very difficult to do. Generally, like when you want to learn general patterns, you need a lot of different type of data, and we're missing simulations to do that. The easiest way at the moment is to train within like one big simulator that has lots of different tasks or lots of different things you can do. Just a beginner doing some important work. Talk about it later. Yeah, sure. It's yeah, let me get some of this stuff done. I will tell you, you're trying to dive in at the deep end as a beginner. Like you're going immediately to like the cutting edge of RL, in which we don't know necessarily how stuff is working. So that's not necessarily a bad thing, but I would suggest that you try working, like you're going to have more fun working on areas where you can at least see some consistent progress and work towards that. If you just try to do that one shot right now, you're going to end up with a lot of difficulty. It's a bit unfortunate how stuck I am on this network architecture. Like, it seems so good in theory. I mean, it's just tough to come up with, like, good reusable network architectures, I suppose. Like, I guess the ideal one, right? The best way of doing stuff, if you can get away with it, is to just, like, have all your data be flat and then just do comms over it. That's not bad. Hold on. Let me think about that. So, the tricky portion with that is, like, your data can blow up quite a lot. Maybe it will help me to try to, if I explain this more thoroughly, maybe I'll get some ideas. And then folks can actually learn some stuff in the process. Let's do that. So, okay. Okay, so there are a couple different ways you can treat your data and encode data for ultra-high perf reinforcement learning, right? Let's say that you have multiple different features. Like, let's say that you have, like, an agent has a type that can be 0, 1, 2, 3, and then maybe it has, like, HP, which is, like, 0 to 100, and then maybe it has, like, some other variables, right? Like, 0 to 5, 0 to 10. And some of these might be discrete, some of them might be continuous. So there are a few ways you can deal with this. The first and the easiest is you can just pack everything into like multiple channels. So you just pack everything like this. What the heck is that? Yeah, there we go. So you just pack everything like this, and if we just like slice it this way, right, then this one goes there, this one goes to here, this one goes to here, right? That's one way of doing it. Now there are some limitations with this. First of all, this is discrete data. It's not continuous. So we don't want to put it into one comm channel. Actually, what this needs is this needs a 1-hot embedding, right? So you can do like 1-hot like this. This needs a 1-hot embedding. So this block of data needs to become 4 channels. But then maybe HP doesn't need to become 4 channels, right? Maybe you do want the continuous value of HP. But then that is difficult because now if you want this to be continuous but this to be discrete, so you have to normalize this, which is kind of fine, but now you have to know which channels need to be 1-hotted and which ones don't, which is a bit tricky. There's also the question of how much we want to commit to a convolutional representation in the first place. Because like this makes sense for the grid environments that I'm doing now. So like if I wanted to, right, I could invest a bunch of time in coming up with a really nice fancy encoder for this. Because if I were given enough time, right, I could come up with a really sweet like 2D mixed discrete and continuous encoder. And maybe I should do that because that would be a really useful tool to have. It's just a bit tricky because I'd have to like write the kernels for it, which I can do that in C, but then doing that for GPU for PyTorch would be really a lot more difficult. But it's doable. But then the question is, is this even a good representation at all? Because this is very specific to grid type environments, right? You might not want to always have grid type environments, right? Maybe the majority of this data is actually going to be entity based. So if you have your agent on your map here, right? And you have like other stuff, then like the one way of handling it is to do a grid based representation like this. So it observes the stuff around it. This is not tic-tac-toe, but it looks like it. But then the other way of doing this is you could instead, if I just draw the same thing, right, you can get an entity-based encoding instead. And there's been some work on that. This tends to be kind of difficult, but you can do it. Because like you need to encode position data in here, and then your agent needs to learn like relative position type stuff. And also generally like relativizing the position is difficult. Not that difficult though. Actually, really not that difficult now that I think about it because I'm writing the environments in frickin' C anyways. Graph neural network, simpler. Entity neural network. I highly recommend this blog post by Clemens. Just if you look up entity-based RL, he has this really nice blog post on this architecture. And it's a good architecture, and I do think it's interesting that he uses like transformer type blocks and he gets high performance, but he gets high performance for like back then standards, right? Like the stuff I'm doing with Puffer now is so much faster than this, it's not even funny. He's got a bunch of fun posts. He also has this one. I really like this one here. Maybe I should get maybe I should ask him about this environment and if he has the code for this open source. Because like adding an RTS to Puffer would be really cool. I wonder how he did all this online as well. I don't know if this is anywhere near as high perf though. Yeah, this is very cool though. What did he use for this? Yeah, he's always doing entity-based stuff here. This is kind of nice in a way that like I actually don't know if these are nice in a way. Having all these separate different little networks is very inefficient. I wouldn't be surprised that this ends up being very slow. It does seem dumb ultimately to bet against this architecture. This does seem like a good architecture. But like this is just a tiny number of samples. Training takes over 2 days, 12 hours. Just over 2 days. About 12 hours. Okay, so 36 hours for 125 million samples. Like 125 million samples in Pufferlib for some of our stuff is like 2 to 5 minutes. And he has more cores. And he's using multi GPU as well. I do very much like this project though. And looking at this is actually a kind of a good thing for like how I'm thinking about architectures now. Got very good work on this. Omniscient value function. Omniscient value function essential is annoying. Appendix. Hold on. So much stuff. Did he open source this environment? This demo site no longer works. I don't know if he actually open sourced the environment ever. I gotta make some decisions here. And the tough thing is like, I'm generally of the camp of just code it, and you'll figure stuff out afterwards. But this is one of the places where it's like I can save myself a lot of headache if I get it right on the first try. Well, I think that regardless, like you definitely want your network operations to be shared. So that thing that he had where all those different embeddings, you really don't want to have happen. At the same time, the entity architecture is so nice conceptually. Hmm. Is it though? Wait. I don't actually even know if the embedding network architecture is nice conceptually now that I'm thinking about it. Because embedding each feature separately, like, that's expensive. Very, very expensive. There are definitely some things that need to be one-hotted. There are definitely some things that need to be one-hotted. Like, the observation map is a really good example of this. Alright, I'll draw up another thing here real quick. So, what I'm doing right now with the MOBA, and I use this approach in a lot of places, right? I have a core map that looks like this. And you could have different entity types on here, right? Like I can have right? I can have all these different entity types. And then the way that you actually process these, this is going to be like 1, 0, 0, 0, 2, 3, 3, 0, 1, 2, 0. Okay, so this is what the network actually sees. This is how one-hot encoding works. And then specifically when we encode this, right? Like the way that this one would get encoded, this is the one-hot representation. So there are 0, 1, 2, 3, so 4 different element types, right? And then what we do is we go to the first one and we shade this one in. And this is your 1D depth-wise network here, right? So this is your one-hot representation. Is this good? The question. I'm trying to think about if this is good or not. Is this 3-player tic-tac-toe? No, this is me trying to explain. So Nathan, actually maybe your thoughts will be good on this as well because, well, actually, hold on. Did you finish your thesis? Oh man, the YouTube delay. In the meantime, so this is not three-player tic-tac-toe. This is me explaining encodings of observations. And I'm actually trying to think about this here because, like, oh, you finished it? Round of applause for this man, please, folks. Heck yeah. Hey, Nathan, if you're down to work on environment stuff at all, throughout this week or whatever, I am absolutely 100% available to help you with that stuff. I would love to see that environment come to fruition. That looks awesome. What I'm trying to do right now, so I've got the MOBA, I've got my secret side project, right? I've got additional stuff that I'm working on. I also just announced Puffer is officially open for business as well today. So, there's going to be some stuff. Holy, people are actually supporting this. Thank you. But the thing that I want to do, and that I think is going to support your stuff and is going to support all the stuff that we're trying to do so much right now. This is the problem that caused me so much grief throughout my whole PhD. Getting good observation representations in RL is so hard. Like, coming up with a good way to format your observation data such that it's easy to put into networks and make fast is really hard. So, like, okay, I have some thoughts on this. And folks, maybe you guys will have some input because this is not a super technical area. This is relatively accessible. So, this is the data. Right now you have 1 0 0 0 2 3, right? So I can encode this. The most efficient way to encode this typically is this is just going to be uint8, right? So this is now bytes. Technically I can compress this even more. If I want to do custom compression, I only need, let's see, there are 4 different values. I only need 2 bits per item here. So I can technically compress this even more, but then I've got to uncompress it, which is, potentially difficult. Maybe once I start writing like custom kernels for networks, for Puffer, once we get into that level of optimization, then we can start looking at that. But for now, this is bytes, okay? And this is not bad, right? This is fine. But what happens is you can see that when I expand this here, not only do I have to have all this memory available, right? Because now I have 4 times this amount of memory. I have 4 of these grids. And if I have like 10 or 15 different object types, what ends up happening is you get this giant ass block of memory. Right? You get 15 of these going this way. 15 different layers. Now that's not a ton because we'll typically have 32 or 64 conv filters anyways, so this is not bad on its own, but having to unpack data like this is slightly annoying. Now, if you just have one of these, it's not that bad. If this is all you need to do, I am happy. But the problem is that this is very rarely the case, right? This is very rarely the thing on its own, because what'll happen is you end up having like multiple layers of this stuff, right? This just says, okay, this is, this type of entity is in this cell. I have like an O here, an X here, a triangle here. Well, what if they have health values, right? Maybe this has, pick another color, right? Maybe we have like HP, and now this has like 3 HP, this has 5 HP, 5, maybe this one has 2 HP, maybe this one's been hit, it has 1 HP, and this one has 3, right? Like, now I have to add channels here. And I either have to add one channel if I want to just put this in as a continuous value, and then I have to handle mixed, continuous, and discrete in the encoder, or I have to discretize this, right? And then I lose precision. So this is kind of hard. This is kind of hard, right? Like, technically, the mixing of different data types like this, some of which require discrete and some of which require continuous, is hard. And also, if you have multiple different discrete types, you end up having to have like this multi-hot embedding layer that like stacks a whole bunch of layers, and it's gotten up to be like 60 before I've had to do. And you lose precision. I don't know if there's a way around it though. Representing this data is hard. You really want the conv layer. Conv layer gives you a ton of good priors about local spatial locality, right? Entity-based embedding doesn't buy you anything. If you were to do entity-based, that does not buy you anything. Entity-based means that you just record an entry for each of these instead of recording like the whole cell, the whole grid, but that really doesn't do anything for you. I mean, it's less data actually, but you still have all the same technical problems. So I think that that's orthogonal. Yeah, it's the mixed continuous and discrete embedding is the problem. Doing that really fast and simple. I mean, technically, I can punt on it and say that I'm going to have to write a custom kernel at some point, right? I actually have not done that before. I have not had to write custom GPU kernels. I've done low-level CPU stuff, but not GPU. I could do that, though. I mean, it's probably nowhere near as bad now that I've been doing all this C. It's probably going to be relatively easy. Technically, it's pretty easy once you write it as well, because it's just CUDA. You can bind it to anything else, right? So I can have it bound for PyTorch, and then if I need it in another framework, I can use the same thing. So that's nice. Conv layers still learn well on sparse grids. Yep. They can learn on sparse grids. What they can't learn on is if I were to just input this whole thing into a conv, like 10023, it can't learn that because the conv, it's going to treat each of those values as continuous, right? So these are discrete values, not continuous values, right? 1 corresponds to something completely different from 2. Like 1 is not any closer to 2 than it is to 3 in this space. So conv is going to be bad for that, which is why you have to one-hot it like this. Now, technically, you don't have to one-hot it, right? There are other encodings you could use. Like, for instance, I drew these in color, right? I could have unique colors for every different type of entity here, and then I could just use a fixed 3 channels and RGB it. Or I could come up with any number of other different embeddings, right? I can use a fixed embedding instead of a learned embedding, which you'd think like, well, isn't a learned embedding always going to be better? Yeah, technically it is possible to always get a better learned one, but you save on memory and therefore you can save on performance by doing it this way. I mean, this whole thing started just because, like, one, the networks are not performing fast enough right now in PyTorch. They need to be about twice as fast as they are now in order to match like the SnakeNet performance. And two, is that I don't want to have to implement all this one-off stuff in C if it's going to be like, if I'm going to just be changing it. I don't want to have to implement all this one-off stuff in C if I'm just going to be changing it, right? Like, what's the simplest thing I can do for now? What is the simplest thing I can do? And I'm always thinking about it that way, and there's like sometimes there's just not a simple thing to do. I mean, I could just like try to implement all these same concatenate and split and whatever operations that I have in PyTorch and C, and I could just like do it that way, but that's not great. That's just bringing all the jank from PyTorch into C. Hmm. It's funny because like this is also like this is exactly the problem that pufferlib kind of solves, right? Like we have off-the-shelf solutions to all of this. And like if you're a company doing RL and you're like using stable baselines or whatever, yeah, puffer's going to be more than 10 times faster just for free and it'll be easier. But like what I'm doing now is like I'm essentially this is the next version, right? I'm trying to solve this problem in a way that's just so much fundamentally faster that it's never going to bottleneck you no matter what. That's hard. That is hard. Um if let me look down one more rabbit hole. So if I were to commit to entity-based data, if I were to commit to entity-based data looks like this now, right? So we had like the X's before, right? So you have one here, you have one here, you have like your, what was this? An O? I forget what this was. O, O. Yeah, and I forget the exact number that we had before, but like the idea is that like you have like the observations for your different shapes, and then you just put them all into a struct so they have the same shapes. This is very easy to code. It's outside of very niche circumstances. It's incredibly efficient. And then this type of thing would be at least easier to write an encoder for, right? Yeah, because I wouldn't have to deal with the additional structured format. I would be able to write an encoder for this much, much more easily. And that would be fully general. I could use that encoder anywhere. How much less data would this be? Quite substantially less, right? Order of magnitude, maybe? At least 80% less data. If it were 80% less data, I could probably get away with a byte for each channel instead of having to do anything fancier. Um, observation encoding function gets a little more complicated. I mean, the observation computation function, but it's not that bad, I think. Yeah, it's not that bad. Not contiguous memory anyways. There's potentially a distance check. Or not. I could just be fancy with the iteration. That's actually very nice. And then what's the network look like? If I had this type of data, let's say that I get these vectors into something that can go into a neural network, then I think it looks something like, this just goes into a transformer, doesn't it? Multi-headed attention. Or if you don't want to do a multi-headed attention, it can go into a max function. That's a fast alternative. So it can go wide and then into a max. I've seen that done before. This is such a good representation, isn't it? Okay. I think what I'll commit to is I'm going to say that in the relatively near future, I'm going to experiment with this type of encoding. And you know, one of the really cool things about deving these high perf sims is I will be able to get conclusive evidence on this type of a thing because the sims are so fast, I can run stuff for so long. I will be able to solve this problem in the relatively near future. So what do I do for today? I honestly think the easiest thing to do for today is to just write it single purpose to neural, not to neural, it's the single purpose to Puffer MOBA. We write it single purpose to Puffer MOBA. And we just copy the operation exactly as it happens. And we see what goes from there. It'll still be a cool exercise. And then I'll have to think about this. I like that blog post by Clemens. I should meet up with him. I think he's still in SF. Probably OpenAI's working him half to death. Getting GPT-5 released or whatever. But he's doing well. Fun. Let's try that. Because I think it's not that bad if I just do it custom, right? I think it's not that bad. Netconf1 input. Yeah, so let's do float, what is it, float star? Float star pre-processed. The size of float. Oops. Now we actually get to start writing some cool code. This goes at the top. So we do, where's batch size? Wait, where's batch size? Oh, num agents. Yeah, okay. Let's just do num agents. I forgot I had to do that. So let's just write this explicitly. So what we're going to do is going to be, we're going to go over the batch size, which is going to be the number of agents. We're only doing this for a single environment in C. There's no reason to do more than that. And then what we have to do is the first 11 by 11, right? One hot. this the correct memory format? I believe so. 11 by 11. And we don't need this J. We just need to do... There are 4 input channels. So we 1 hot. So let's do int in adder. Batch size times 11 times 11 plus I times not times 19. There are 4 input channels. Again, I always forget to sketch this stuff so people can follow my convoluted thought process. Let me sketch this out for you guys real quick, just so you can follow my... I'm going to do this once so that people can follow this and actually learn something from this exercise. So right now the input looks like this. Okay, this is 11 by 11 by 4, which means that in the memory layout... Hold on, let me think. Yes. So this is 11, 11, and this is going to be the grid data. This is grid. And then what we have here, had to step away. Definitely work on Dopus this week. Hey, Nathan, like, you swing by and let me know if I can help you out, okay? I've been doing lots of stuff with this. I've written so much low-level code in the last few weeks. So let me put it this way. The next update to Pufferlib is going to be bigger than the current size of Pufferlib, and it's like all this C environment sim code. So we're going to have ultra fast environments. Like literally, like the MOBA is going to be 2,000 plus, and then the other environment I have looks like it's going to be 3,000. Not to mention that we're going to port like you and Noah's Atari games. I'm going to help you guys port those to native C so that we can have them on web. And of course, you'll get the credits on the website as well. If you want to contribute them, that is. C makes it... Nope. C doesn't make it any faster. You're A-okay to write in Python. C is just for WebAssembly. So if it's easier for you to dev in Python, keep deving in Python. I don't want to make your life any harder. It's gotten to the point where, for me, it's just as easy to write C as it is to write Python. And WebAssembly, right? Play online. Plus, I'm writing all these networks in C, so it's literally we can do inference online too. Okay, let me finish my thought process though, because I was explaining how the encoder that I'm writing has to work here. So this is grid, this is continuous data. That's an N. And then this is extra. And this is just 26 features. So what I have to do is I have this big block of memory that this is going to get written into. It has to be 11 by 11 by... Hold on. Do I have this right? Linear memory layout is so difficult to keep in your head. I think I have it right. Because it goes row, and then it goes... Yeah. Okay, this is not as bad as I thought. Yeah, this is not as bad as I thought. So, here. This 11 by 11 grid, this is what's going to happen. This is going to become 11 times 16 here, and this is 1 hot. And then this gets normed. And then this is going to just stay 3. And then this gets normed. Norm. I can't write. And this goes here, 26. Okay, so this is what we're writing, is that we have to take this and do these operations very efficiently. Make sense? That actually did help me for once to think about what I wanted to do. Because now I actually know how this should work. Because this is going to just be plus I out adder times 11 times 11 times 19 plus I. Now this one is I times 19, right? Except it's not 19, right? Is it 11 times 11 times 19? Wait, in address plus 26. We'll make sure all these numbers are not hard-coded, once I finish this. Plus 26. So this is the size, your in size, your out size here, right? And then the out address does have the out address have things to worry about? Plus I times 19. It's 11 times 11. I times 11 times 11, I believe. Is it 19 here? It is 19 here. Man, it is hard to do this in your head without messing this up. And then you do pre-processed of in address, which is, wait, what? Yeah, net pre-processed. Net pre-processed out address. No. Out address. Wait. Equals. One adder. Input. Right? This is your one hot address. Out address plus one hot adder. 1. And this how it works? You have to clear your pre-process buffer. And then you set one hot. Okay, so if this is correct, then from here, wait, for out address plus, and then you do net out address Why is this so hard? It's hard because of the way that the layers are ordered. It's difficult to think about. I should make some tool that just like, you know, takes all your memory and then like just colors it differently so you can see where stuff is. That'd be really easy actually to do. Wait, wouldn't the easier thing... You know, I've actually been wondering, like... Maybe this is me being dumb, but can't I just cast this to be like a 4D tensor and then just directly index? That should be the same, right? Well, I still have to do the input, but like the output address, can't I just cast this to be a 4D tensor? I think I can, right? Let me go find the syntax for that. Because I don't think that there is a reason not to do it like this. Hold on, I always forget the cast syntax. This is a cool trick, but I always forget the syntax because it's very obnoxious syntax. Did I not even use it in here once? I know I used it in the MOBA source code. Yeah, right here. Float star pre-processed. And then you just shave off the batch dimension, and then you do 11 by 11 by 4. Oh, and it is an unsigned char star, isn't it? That was almost bad. Unsigned char. And net pre-processed. No, it is float. What am I doing? Float. Float. Net. Technically, I can just do all of it this way, can't I? Or no? No, the memory's not contiguous. Okay, I can still do this, though. So, by doing this, now I have 11 by 11. It's not by 4, right? It's by... Oh, shit. No, now I remember why I can't do this. God damn it. Because of the 26 at the end is the problem. The 26 at the end is the problem. Well, hang on, though. I need two different tensors anyways, don't I? I literally need two different tensors anyways. So... I can do this. Map. So this is like obs 2D. Float obs 1D like this, right? 1D, 2D, 2D, 1D. Obs 2D. Obs 1D is going to be 26. Yeah. So now what I can do is I can do float star obs 2D. And then this is going to be size 19. 19. This net is going to be obs 2D. And then we do float obs 1D. Now isn't that nice? Now we actually can index things without going insane. Because I no longer need to care about this out address, right? I literally can just do BI. Okay, I need to do for J now instead. I write an extra loop, but that's fine. Oops. Okay, so we do J. Whatever this is, whatever, tab. We're going to fix these addresses, and then batch IJ. And then this here is going to be like one hot IDX equal to 1. And then all I have to do is figure out the in address, which is going to be batch times 11 times 11 times 4 plus I times, hold on, I times 11 plus J. I think this is correct. Right? Yeah. And this is one hot IDX. Almost. This tells you the value. Adder. If only C had passed by reference. The syntax so clean. Pointers aren't bad. Took data structure in 2012. The pointers actually are not bad. The one thing I really hated in C is the pass by value by default. Right? Now I just use pointers everywhere. I just use pointers everywhere. And I don't think I have a single place in my code where I do like star thing dot. Like I don't have a single place where I'm ever like directly dereferencing something ever. Right? So once I realized that, it's actually not bad at all. Like when I make structs, my structs, well, I guess for performance this is maybe a problem. So I might actually have to revisit this. But like I pretty much never will make a struct that contains a specific thing. It'll contain a pointer to a thing. That's actually kind of bad for perf now that I'm thinking about it. Yeah. But not really. We'll be able to make it fast either way. Okay. Okay. So here's your one hot. And then you got to do some more iterating, don't you? I got to figure out how to copy the last layers. Where are those laid out in memory? I'm trying to think where I put this in the loop. Int batch off. This is going to be, because we're going to need this anyways. Actually, this offset is good. So we'll just make this extra thing, and then I think what we can do is... Am I crazy, or can I just do this? Obs 2D. So this is going to be 16 plus... Well, this is just, wait, 16. And then this is going to be input. No. 2 times. Three. There are 4 layers, so it's 4, yeah. Does this not just do it? And then at the very end, you have to do... times 11 plus I. Yeah, then you have to copy the 1D data. So I think that this does it, and we have to add some stuff to this, but I think that this is it. So I think that we just basically... Obviously, we have to clean this up. Obviously, there are a bunch of hard-coded constants. But in, what is this, like 10, 15 lines of C? I think we have this entire pre-processing mess done, and done like ultra efficiently without doing any extra copies. Now, this is incredibly error-prone and needs to be tested and all of that, but I mean, if this works, right, it's solid. So I think that what we do is, this one is divide by 255.0f. That's what we have on the right screen here, divide by 255. And then these are also divide by 255. So that's the pre-processing. Cool. And then what we do is we can do conv2d. This is going to be net pre-processed. It's 2D. obs2d, because you need the raw pointer for this. And then we do relu conv output, conv2d, linear, flat. This is your whole thing. So right now we are at flatten. And then flat is going to be, oops. This net flat here is actually obs1d. obs1d. And then we have to do concat on dim1. Oh, we copied this into the wrong channel, didn't we? That's awkward. But is it cat1d? Hold on. Yeah, it is cat. It's cat within one. Map stack. Cat dim one layer. Oh, I see, because it's pre-allocated like this. So it's net obs 1D, which is not what we want. This should be net conf2 output, net flat output, right, like this. So these get stacked. And then that's not map stack, is it? What's the concatenator? Cat 1D. $128 and 26, is it? No, 32. Oh, wait, is this actually conf rel? No, it's CNN channels is 32. So this is 32. Ah, yay. And then this is net cat. This is net cat. And then what do we do from here? Proj, I think. Cat, it's proj. Oh, it's relu. It's relu proj relu. Is there a thing for relu? Wait, why is relu a layer like this? Ah, because it has an output buffer, that's fine. Okay. So now we do relu. And then we do linear to proj. And then we do relu. And then this gets LSTM'd, right? We have the LSTM in here. Thought we have a wrapper for this. Yeah, input here. Proj. Okay, now we do LSTM. And then the decode, right? Which is the discrete decode for now. Linear net actor. Value function. And then what is the multi-discrete? Argmax multi-discrete. I don't think that signature is right. Yeah, argmax multi-discrete just takes the input. Discrete net actor output. Okay, and then that gives you your actions. Forward. And this gives you int star, I believe. Int star forward. You actually don't even need the value function, but we'll leave it in there for now. That multi-discrete output. So we're gonna have to debug all this, but this is the basic form of what we're going for. And yeah, there's some housekeeping and stuff, but if you look at the code, it's not really any longer. I mean, obviously, like, they use the one hot and stuff here, but there's, like, all this indexing mess. It's really not that much longer or more ridiculous compared to the torch code, which I find kind of funny. Holy, he's done pretty well. What on earth are they doing? No idea. Oh, I've totally missed messages from them, haven't I? That's okay. I gotta finish this first. Gotta get the code release, am I right? Okay, so let's see what is potentially missing from this. Or if I think I have this remotely correct. Well, first of all, we gotta get the layers cleaned up. So we have net. So we have conv, relu, conv. You don't need to flatten. And then what do? We do linear, flatten, concat dim1, cat. And then you do relu, proj, relu. And then you do LSTM, like this. We don't use one hot now, so we'll ignore this. So num agents, obs2d is going to have 19 channels. Obs1d has 26. You do this conv2d, relu conv, relu conv. Yeah. Flat. Cat. relu 2, proj relu TM actor. Okay, looks good to me. And then the one thing I know I definitely did wrong here is I have the channels in the wrong order. So it's channels first, right? Is that how I implemented it? Tell me that's how I implemented it. Did I do channels last or channels first? Wait. Yeah, I did channels first. So this just needs to be one hot. Man, it's so nice to have this indexing like this. This is 17, 18. Okay. Yeah, that's good. So if I can clean this up a little bit, we have it's conv relu conv, and there's the linear layer, and then it's cat relu linear relu, and there's the LSTM, and then it's an actor value, and then we have, oh, I need our multi-discrete, that's what I was missing. Okay, we got multi-discrete, and I think it's at 23. Hi, why do you have an LSTM in your MobaNet, and what is MobaNet purpose? So the purpose of it is to run this environment. These guys don't move at the moment. They need to be, they need their policies. And the policies are trained with a conv and an LSTM. So if I want them to actually be able to play this game and do cool stuff, then yeah, we need to actually get this running. And now it does work in PyTorch, but in order to run this online, we want to have like a little C-only demo. So that's what we're doing at the moment. This is somewhat more complicated than I expected it would be, but hopefully not that bad. We'll see how bad it is to debug. We'll see how bad it is to debug. The only thing I'm missing is loading the weights here. So why don't we step env. Let's do MobaNet. Do I have all this stuff? Literally, I don't need any of this, right? It's num creeps, num neutrals. Literally, the only thing I need here is num agents. I don't know why it did all this autocomplete on the signature. Yeah, so num agents. So we init a MobaNet num agents. Then this will be free MobaNet. And then I have to do forward, right? Where's obs? I need to env. It's like env obs or something. Oops, it's moba.h obs. Oh, do I literally have these stored separately? I literally have these stored separately, don't I? Env observations map, env observations extra. That's super nice. And is it unsigned char star? I believe it is. It's char star. Oops. obs2d, and obs1d, obs2d, 0, and then float. This does not need to have obs2d like this. Does it? Oh no, it does. Yeah, it does. So this right here, input, this is env obs2d, 2d, 2d, obs2d, obs2d, obs1d. Cool. Now you can pass this, and then you can do, cool, welcome. And then this is now forward. This is net, and this is env obs. Is this what they were named? View. No, it's observations map and observations extra. There we go. So now we have these forward functions, right? And is there a... Do I have to write these into the environment actions? I think I do have to write this into the actions buffer, so let's do that. Then this has to be int star actions. Argmax multi-discrete. Well, maybe I'll just copy them for now. We'll just copy them from here. Copy. Test is going to be n. Yeah, no, this is going to give me garbage. I don't really want to do a raw mem copy there. I know what I can do. So instead of giving this an output, let's just comment this for now. And what we'll do int star output. Okay. Nope. We don't need to free it. Wrong one. We'll do int star output, argmax, and instead of layer output, this will just be output. All right. And now what I can do is when we init the multi-discrete here, we go to use it. This will be actions. Actions. This becomes void. This gives you int star actions. And now all I have to do is now this will write directly into my buffer, into the actions buffer. And then you can step the environment, you can render your game, and you're good to go. Now we have to fix all this and get it to work. Let me make sure I'm not missing anything important here. Hold on. People are saying my puffer boxes are down. Let me go check the puffer boxes. That would be unfortunate. I have this like mini cluster for Puffer, but it's like literally in the garage. Well, shit, none of them came back up. That's bad. That's real bad. That kind of throws a wrench in everything now, doesn't it? I'll have to deal with that later. Well, let's start testing this at least. Okay. Let's figure out what's wrong here. Incompatible. Two. What? Okay. Multi-discrete. Come on, this shouldn't be that long to debug. Wake up here. Where's the H? Argmax multi-discrete. One warnings, two errors. No member name. Preprocessed. One hot. So somehow it's make, not init. I use make when I return the struct, and init when I give it the struct. Okay. Make relu. Batch size input dim. What is this? 3. 32 times 3 times 3? 3 maybe? And then this one here is 32, 28. Make this is make argmax multi-discrete. What in the hell? Auto-completes, man. Int logit sizes. Hold on. Int logit sizes. Yeah, that's fine. Batch size, logit size. Some actions. This, and I need to actually get this from. Where is it? Actually, what am I doing here? Torch. Do I have the sizes here? Action dim. Seven. Okay, here it is. So int logit sizes of 6, 7, 7. And now this is on the stack, but the thing is it gets copied to here, so we have it done very nicely. And then did I get to 23 right? This is 14, 17, 23. Yeah, perfect. And then this is going to be logit sizes. Like this. Oh, and then the number of actions, this is 7. This is 6, right? You have to give it the 6. Art max. Is there an underscore? I think there probably is, right? Okay. 5. We allocated this the wrong way. This needs to be 19. Like so. Compiles. And we get a segfault, of course. Right here. Okay, so we have the 1 hot index here. 255. So 255 is not a valid 1 hot index. Yep. That'll do it. So either the data's wrong or the offsets are wrong, and either could be the case because we haven't tested we have not aggressively enough tested the compute observations function since we changed stuff. Wait a second. Batch offset's wrong. Yeah, because the input's 4 channels. Okay. Batch offset. Yeah, no, this batch offset's wrong. This is simply 26 times, or b times 26 plus I. Still wrong, huh? Are we sure about that? Yeah. Batch offset looks good. Element offset is also good. What about the 2D one? 19. 11 by 11. Yeah. So the issue is that 255 in there. That should not be able to be 255. Somehow that's a max byte. I wonder... Hold on a second. No, it is an unsigned char. 11 by 11 by 4, the batch size. You're not zeroing the map right now, which is probably really bad. Zero I less than I plus plus extra 0 Same memory. It's fine. Okay, so now we should